Okay, welcome back. So now we will study a thing which is interesting, mostly if we do neurophysiology. So recordings of electrical signals, very weak electrical signals from a population of neuron, or even from a single neuron, like in patch clamping. So we want to understand one concept which is very important in neurophysiology, which is the concept of impedance of an electrode. And for this we make a model, a simplified model of an electrode, just to be able to understand what this impedance means and the consequences of the value of this impedance. So now what do we have here? We have a situation where we have a container, which is this thing here, this container. It's like a beaker, but it's not manufactured in glass, but instead this time is manufactured in metal. So it's a very good conductor, let's say a perfect conductor in this simple model we have. So it's like a pot, metal pot, and then you have something in it. So what do you have inside this thing? It's a fluid, so all over this region it's a fluid. So this is the top of part of the fluid, and this fluid has two characteristics. So one characteristic of this fluid is the conductivity, G, which is 1 over rho. So this fluid can conduct electricity, but it is also in part an insulator. So it's a mixture of things. It's not a pure conductor, not a pure insulator, and usually let's say it's a sort of maybe ionic conductor, like you have water, distilled water, pure water, which is a very good insulator, and you have some salts dissolved in the solution. The more the concentration of the salts, the more the conductivity G. So if we remember the resistor, we have to go back quite a lot. Here it is. So we said that this barrel is a sort of cylinder with something in it, and we call this thing ohmic conductor. We had our famous Ohms Law, and because of this law we had that V equals R multiplied the current I, or conversely, let's say I equals V over R. Then we have also the so-called local form of this thing, which is written here. The current density J equals 1 over rho, the electric field. Rho is the resistivity, and we said that this thing can be called G, conductivity. So J equals GE is the equivalent of this thing. And then we also have to remember the capacitor. We said that the charge Q, which can stay in a capacitor, here and here, positive and negative in front of each other, is the capacitance multiplied the voltage, and the capacitance has something to do with the geometrical arrangements of the plates and the shapes and whatever, but there is a coefficient we called epsilon 0, which was the dielectric constant of the medium between the capacitors, the place of the capacitor. In this case 0 means we have a vacuum, here there is nothing, but if we have an insulator material, this epsilon should be replaced, epsilon 0 should be replaced with a certain epsilon, which is epsilon 0, the dielectric constant of the vacuum, multiplied epsilon r, the relative dielectric permittivity, which is a parameter that comes with the type of insulator we have. So if we have a distilled pure water, that one will have a certain epsilon r, and this thing is connected to this formula, giving us the capacitance and then therefore the charge. So if we go back then to our case here, okay, so we are in this situation. So we said we have an external metallic container filled with a fluid characterized by two parameters, g and epsilon. Then what we have here is a sphere, which is a metallic sphere, perfect metal, so with conductivity, resistivity G equals 0, and then infinitive conductivity, as well as the case here. Then we have another thing, which is a perfect wire connecting this electrode to the battery, to an external battery, having amplitude voltage U. The sphere has a certain radius, and one important thing is that this wire here will have a coating, so it will be insulated. So just to be more clear, it will be something like this, like this piece of wire here. So it has an inner part, the metal, and then a sort of jacket which is preventing the metal to be touched by something else. So imagine that here you have this situation like this. You have a piece of wire, so the inner part is touching the sphere, but the liquid cannot touch this. Okay, this sphere is what we call electrode. So it's an electrode which is inside a fluid. The electrode is connected to the positive pole of a battery. The metallic container is close to the negative pole. There is a little bit of conductivity, and so there can be some current exiting from the electrode in all possible directions, reaching the container like this. So in an ideal case, if this container is infinitely big compared to the radius of the sphere, so this sphere would be something like in the middle of an ocean of fluid, and those lines of currents, streams that are, let's say, exiting, the current is flowing like this, so it's flowing like this, then out of it, then it will reach this, like this, in all possible paths you see, for instance, like this, and so on. So in an ideal case, now I make a little drawing like this here aside, those streams of currents are basically exiting radially out of this sphere. Of course, this is a simplification. Okay, so let's try to write some equations. If that is the case, then we know that the current J, current density, equals the conductivity G multiplied the electric field. Then by knowing the electric field, we know also the current density. And in a simple case where you have a point charge or a spherical charge, meaning a charge which has been put on a sphere, by the symmetry of the problem, which has a sort of central symmetry, we can easily write the electric field like this. It's the Coulomb law, so one fundamental law of the electromagnetism that can be verified. So Q is the charge on this sphere, R is the distance from the center of the sphere, it's small r, the big R is the radius. So this problem is a spherical symmetry, so we can work in spherical coordinates, which means that the strength of the field, electric field in this condition, does not depend on the angular position but only on the distance r. So it's a one-dimensional problem. Then we can remember that there is a concept of potential, let's say the voltage, which is minus the gradient of the electric field. No, sorry, wrong. The electric field is minus the gradient of the potential. And we said that in one dimension this thing is a derivative along that direction, so it's minus the phi over the r. Now we call V this voltage potential. But we know the shape of the electric field in this simple case of spherical symmetry, and therefore by writing this we can integrate this thing, and this gives us the voltage, so the potential, as a function of the radius, and which is this thing. So if we plug this into this, we can find this result by integrating from small r to infinitive. So here we have the potential, the voltage, as a function of the distance. And if we compare this last thing that we have obtained by this calculation that comes from this definition of voltage, this, if we compare this one with the expression for the electric field, then we see that they are very similar, kind of the same. There is only 1 over r factor that makes them different. So if we compare them, we see that we are in this situation. So we made this transformation in order to be able to connect the electric field with the voltage as a function of the distance. Now we can remember this thing that we know, the Ohms law, and we can remember the definition of current. So we had a cross section lots of charges passing through a certain cross section having a area S. So S is the area of this cross section. These are the charges moving in the conductor. Now you have to think that the flux is like this. So it's a sort of spherical thing, and the current is exiting like this in all directions. So this cross section would be the cross section of a spherical object. So the current is exiting from this cross section and reaching this point. Then is passing through that spherical cross section and reaching another spherical cross section like this. So it's exiting like this. So now this surface S is not flat, is curved around the electrode. Okay, so we are here. It means that in order to get the current, we have to integrate the current density through a surface S, which now is a sphere embedding the electrode. So let's write the definition of current, but let's put this in place of J because we know the electric field. So we make this substitution. Then, because this problem is, let's say, domesticated, it's beautiful. It's in the spherical symmetry. This integral is easy to be done because the lines of electric field are perpendicular to the spherical shape we choose as the cross section onto which integrate the current density. It means that this thing can be simplified in a way that the surface S is the surface of a sphere of radius r, and if we have a sphere of radius r, then the surface of that sphere is 4 pi r squared. Then this is a constant that comes out of this integral, but everything is kind of constant because in place of E we put this V over R, and because we do this integral on a spherical shell, let's say, we can decide to do it in every possible of these spherical shells that we have here, because the flux is the same. So we know that the charge is conserved, you cannot destroy charge. So the charge that is exiting out of this spherical shell and moving through the sides of the metallic beaker is passing through this cross section, but also to this one and also to this one. It means that the current which is exiting from this surface is the same of the one which is exiting from this surface, which is the same of the one which is exiting from this surface. Is always the same charge that is moving. So we can choose to calculate that current exiting out of, for instance, this surface here, exactly the one which is in contact with the sphere of radius r, because we know the voltage of this thing, which is U. It's connected with a wire to a battery. So we take advantage of this knowledge we have, and in place of E we will put V over R. Now this time we will compute E of r equals V of r over the radius of the sphere. So we are choosing to integrate on this surface. And what is V of r? So V of r is the voltage of the sphere. So it's what we called U, because the sphere is connected to a known voltage U, the voltage of the battery, which makes the current flowing out of it. So if we substitute all these things, so E would become U over the radius r of the sphere, and here we have this r squared, so it's G multiplied U over r multiplied 4 pi r squared. Let's write it. It was this G multiplied U over r multiplied the surface 4 pi r squared. And if you simplify this, then you get the result. It's quite, let's say, complicated. We have to be careful in all those passages. So we were able to calculate the current flowing in this circuit, which is the same current flowing in the wire and the same current that is entering in the battery and then going back to the metallic beaker inside all the fluid and then in the sphere and so on, by choosing a very particular simplified geometry that allowed us to do these integrals in a simple way because of the spherical symmetry. So now that we know the current, let's analyze this current. It's a constant 4 pi multiplied r, which is the radius of the sphere. It's not the resistance of anything, it's the radius of the sphere. G, which is the conductivity of the fluid, and U, the voltage attached to the electrode. And so finally we can compute the impedance of the electrode. By definition, the voltage of it by divided by the current exiting out of it, and we obtain this result here. 1 over G is rho, the resistivity of the fluid, and so what we get is that the impedance of an electrode is a resistance. We call it R electrode. It's a resistance because it's a real number, so it doesn't come with an imaginary part. And this resistance is proportional to two important things. The resistivity rho of the fluid sorry, and the radius r of the electrode. So there is nothing about the resistivity of the metal of the sphere nor the resistivity of the wires that connects the sphere to the battery. It depends on the property of the fluid and the geometry of the electrode. So we see that now for a given fluid of resistivity rho, and also we notice that it doesn't depend on the dielectric constant of the fluid, but it depends only on the resistivity of the fluid. But the important thing for us to remember forever is that the resistance of an electrode is inversely proportional to the radius of the electrode. So if you have an electrode like this, let's make it big. This would be an electrode like electrodes usually are something like this. like a pen, so they are long and then in the end they have a tip, and the tip is exposed while the shaft is insulated. So we have this situation like this. So the tip is exposed and all the rest is insulated. So this tip here, we can approximate it as a sphere of a radius r, and then we see that the sharper the electrode, the higher the resistance. So with this model in mind, we can think of modifying the shape of an electrode. We can manufacture the electrode sharper or less sharp, and by doing this we will modify its impedance. So one technological method to change the impedance of an electrode, for instance, is to plate the electrode. So if you put the electrode in a solution, so-called gold plating solution, for instance you have gold, then the ions of gold, by the application of electricity, can migrate to the solution and can become attached here to the tip in layers like this. So then in the end of this electroplating you will have a gold layer which adds to the original let's say part of the exposed tip of the electrode, and this can make the radius becoming bigger. So let's say radius plating can be bigger than radius original. So by electroplating an electrode you can easily change its impedance, and this we will see it will be useful in order to tune the properties of our electrophysiology recordings.